Okay, hi everyone. I hope you can hear me correctly. So I don't really see the audience, but yeah. If you guys have any questions along the way, ask away. I don't mind you interrupting whenever there are questions. So yeah, let's start this wonderful event. And thank you so much to Pakistani Women in Computing for giving me this opportunity. This is really amazing. I've been part of this community in the Toronto chapter for a while, but yeah, the celebration of women in physics and women in engineering and computing. It's definitely this whole month is dedicated. We're dedicating it to that, and yeah, hopefully we can inspire and encourage young girls and all across our community, all over the globe, to also think about careers in STEM and how we can also make impact. So yeah, today maybe I also want to introduce myself a bit. So my name is Aroosa, and I'm a graduate researcher at University of Waterloo. I also work at the Vector Institute of Artificial Intelligence in Toronto. So my interests and work lie on the intersection of machine learning and quantum physics, quantum computing. And I've been in quantum computing for a long time now, 6-7 years in research, and it's quite amazing just how fast things have changed just in even in this small time period. So yeah, we'll talk about that, the exciting things that are happening in this field. And yeah, I try to make the talk not too technical. I give examples and overview of general things, but please feel free to ask any questions. So yeah, I am originally from Pakistan and from Lahore, and these pictures are just like a few glimpses of the wonderful, wonderful cultural diversity and cultural beauty we have in Pakistan. And I just wanted to give a shout out that women on this celebration of Women's Day. Yeah, I hope there are Pakistani women in the audience, and also if you're watching it later on, yeah, I hope you get inspired, also not just by other women, but also yeah, our culture and everything. It's yeah, it's quite a beautiful country. So I was just missing it. um, so, oh, I see. I have two slides going on. Okay, so yeah, the pictures are here. Yeah, so different glimpses of our culture. I have two slides going on. Okay, so a bit of history about myself. Like I said, I have been in physics throughout my academic career. I did my undergrad from it's university in Pakistan. I did that in physics and computer science, and my sort of specialization was in quantum optics and quantum formation. And then I went to Germany to do my master's at Ulm University. If you have any questions about that, I'll be happy to answer that as well. Then I took on my first PhD at ETH Zurich, and that was in topological quantum computing. After that, so yeah, there's also a bit of non-linearity here in my career, which yeah, which also we'll talk about later. But essentially, I changed my field a bit from experimental quantum computing to computational quantum computing. So yeah, I moved from ETH Zurich to then Toronto, and I then worked as a quantum machine learning scientist at Xanadu. It's a very, very nice startup in Toronto. They do a wonderful amount of wonderful research. They're really at the cutting edge of quantum machine learning and quantum photonics. If you have any questions about that, please feel free to ask. So I worked there for a bit, and now I went back to grad school again to University of Waterloo. So yeah, it's been a bit of, I've worked in many different areas of quantum computing and tried to learn a lot of different things. And my path has not been linear, but yeah, it's been a lot of fun. And yeah, we can later on discuss a bit more maybe. So in the talk, I want to talk generally about quantum computing, why we should be talking about it, or why it's exciting, and then how it's impacting, or how machine learning and AI is impacting quantum computing. So I'll give you two perspectives on that. One perspective is where machine learning is helping us understand physics or do physics, and the other perspective is where quantum computers or quantum computing is trying to help machine learning understand it or enhance it, speed it up, or these different aspects. So there's this two different areas that are very that can have a lot of impact. And then later in the end, of course, we get this unique opportunity to talk about women, and I'm from physics, so they're definitely talking about women in physics is a very good opportunity here, because it's not so many of us in there, so we'll talk about that in the end. So yeah, quantum computing is quite a hyped up word right now, and quantum machine learning as well. You see a lot of news articles every day appearing in all different kind of journals about how it's going to change the world. There's like a revolution is going to happen. So depending on the application, there's some people talking about cryptography, cybersecurity, how it's going to change drug design, material design. What would happen in 10 years? Would everything change to, like, would your laptop be a quantum computer? What would happen? So these are a lot of exciting news and conversations happening all over the world right now. So I just took some clippings to give you an idea. And so the effort also worldwide has really increased. Quite a lot recently. So when I was doing my undergrad, and even just 10 years ago, quantum computing was very theoretical, and the experimental part was mostly in the universities, and there's a lot of extremely hardworking, brilliant physicists working all over the world to get these technologies, to push the limit bit by bit. And now it's starting to roll over and spill into broader categories and aspects of society and industry. So there's been recently like a huge kind of recognition of this fact, and a lot of governments and companies are starting to look into this and invest a lot. So it's just here present like a picture of this worldwide kind of effort to understand and keep up with this technology. And also just like a snippet here I give about I think this is just from US, about the private sector funding in quantum tech. So you have software, you have hardware, you have security, you have communication. So all of these areas that are depending on computing and information can be affected by quantum physics. And then what do you do when you bring in quantum computing, quantum physics? So all of these areas are starting to get a lot of attention in the industrial sector as well. So this is just to motivate you, because I suppose we have a very broad audience, that even if you don't know what's happening inside, like what is a quantum computer, and you've heard the term, it is definitely something we should be aware of and be cognizant of. So yeah, just to give you that kind of perspective. So I'm an academic, or a young researcher, and I'm not going to sit here and kind of try to decode which news article is correct and which promising application will be happening in 10 years or 5 years or this and that. So I'll just sort of educate you about what this really is and what is happening in the background a little bit, just an overview. So here I'm going to talk about the outliers, the outlying principles of quantum physics or quantum computing that makes it different from what we have classically. So what's in your laptop, what happens when you go to a quantum computer. So yeah, I just mentioned the unique principles and not like everything, because that would take months to get into. So maybe we slowly build up. So we build up the history, go back a little bit to why quantum and how it started. So basically what we're seeing around us, the observations we make, we try to explain it in physics, right? And it turns out that as we got better at experiments and as we pushed technology in like till a century ago, there were a lot of phenomena that we could not explain with the apparatus or the knowledge of physics we had at the time. So for example, there was this really very simple but really interesting effect that we cannot explain. It's called photoelectric effect. Essentially, you shine light on something and you expect that the electrons get energy and they won't escape the material, and you expect that it happens at whatever, whatever kind of light you shine, and whatever energy, however intense you make the light, however powerful, it should happen. But that's not what you see. It actually happens in only at certain wavelengths. And so this is something we could not explain just using classical physics. So many such examples exist, where, especially when we go to smaller scale in our materials, we weren't sure how to explain that, or the classical physics was breaking down. So that sort of is, the birthplace of quantum physics, where we try to explain behaviors and phenomena at small scale. And yeah, that led to like this whole many decades of development of quantum theory. And yeah, so we don't have to like worry about what exactly is happening here. And so to keep it general, then in the 80s, for example, we were quite advanced now that we could, study single molecules. We could try to control or shine. We had lasers now, we had microscopes. So a lot of very wonderful technological advances happened in these between these two time points. So yeah, with the help of these things, we're able to control very small systems or talk about it. So then this very brilliant scientist Feynman came along, and he proposed that, it's hard to study quantum systems, but what we can do is, like, if we can control some kind of quantum system, like something we know, like a single atom or a couple of ions, if we're able to control how they talk to each other, and then we can try to simulate bigger systems. So for example, if you want to study, let's say, how glass works, or how a certain material changes its properties with temperature, and you want to really understand what's giving rise to any of these observations, any behavior in this material, you have to go down and look at the microscopic level. And that's very hard to do, because so many, you have billions and billions of atoms interacting, and it's really hard to solve that on a paper. So the idea is to use a system, a model, and use it to study a material then. So if I have two atoms, I can sort of induce or try to induce interactions the same way the material has. So I can sort of simulate or emulate, copy the behavior. And then when this smaller system that I can study, that I can control, I'm able to, model the physics of the bigger system. So that was kind of the idea behind quantum analog computers, or quantum analog simulators. But the one very wonderful thing that came out of it was that if we have controllable systems, if I can control a single atom, then what if we use it to encode information? So not just like interactions, but what if I encode information of certain channel into this? So this sort of led to the birth of quantum information theory, quantum computers, and so much progress has been made. Such amazing work has been done in the last just this 40-50 years, that now we actually have small systems, small quantum computers, which have up to a certain number of atoms that we can control to a certain degree of accuracy, and we can talk about quantum computing very in very vivid terms. So a lot happened over this 100 years, and yeah, so we'll talk about this in a bit more compact form. So yeah, like I said, this is just an example of what different quantum computers could look like. Maybe you've always seen like this kind of image where maybe you don't know what it is, but you see all these wires. It's basically a dilution fridge, and you have a sample inside, and it basically you're trying to cool something to very low temperature. So you're isolating all the external like disturbances, and we can then study something we want. So yeah, it's just like there are wires going up and it's just for communication. So yeah, I just wanted to like show you a picture of other kind of quantum devices and computers that are also possible. So this is like a popular image, but other devices are like using photons. So this is a photonic chip. You basically send in very small, limited, you can say energy packets of photons of light, and you can control them using certain. You can yeah, we can control the way they interact with each other. Um, you can have trapped ions. So this is basically you have an atom and it's an ionic form, so it's like a charged particle. So you can control it using electric fields, and then you can shine laser and excite it into different levels. So these are all just different examples. So this is very interesting examples. Diamond. So if you it's yeah, when I talk about this, some people get very excited that, oh, you're working with diamonds, but usually it's synthetic diamonds. But essentially what you have here is you can when you have defects in diamond, you have like certain, let's say there's some missing atom there. It gives rise to certain like molecular states in the diamond. So it's essentially, it has carbon atoms, and those carbon atoms have electronic levels, and we know the electronic structure. And then we have a lot of them, and they have this, we can make this molecular sort of picture of how all these molecular states are of, let's say, a group of atoms. And let's say one of the carbon atoms is missing, and then this sort of disrupts this molecular states. So this is very interesting. So in diamond, essentially you can these states are very isolated because diamond has a very large band gap. And then it turns out that you can also sort of exploit these very isolated states and use it to encode information. So I'll go into detail of what I mean by encoding information and what exactly is happening in these devices. So just to give you a very, I'll give a very, try to give non-technical, not too crazy, detailed explanation of quantum physics or quantum mechanics. But yeah, it's basically, if we talk about information theory or encoding information, you have classical bits, you have either zero information or one bit of information. And it's when you go to a quantum bit, so let's say you take a single atom, it could be carbon, or let's say, this very, one very popular example is Rydberg atoms, because they're quite huge. And yeah, I won't go into details, but if you have questions, please ask. So yeah, you take an atom, and let's say it has two levels, two energy levels. Then we can say that, let's say, it just has one electron, very simple atom, like hydrogen atom. But yeah, we make this toy example. And let's say it has two levels, and when we encode the information, right? This is an arbitrary language we developed. So we say that 0 is 0 information, and one bit of information is, it represents a certain amount of information we gained. So now we change our language to say, okay, if the atom is in the lower energy state, then it has zero amount of information. And then if it's in the other or higher excited state, it has one bit of information. So this is how you can sort of encode information into a physical quantum system. Another example could be a photon, which I said was like it's the packet of energy. It's just the smallest, is what light is made up of. So basically, if you take a laser, if you look at what light is coming out of your bulb and you break it down, you will see that it's made of these packets of energy called photons. So you take a single photon, and it could be, maybe there's something called spin. So let's say it's like a ball. It's a very, very crude picture, just to help in our understanding. So we have, so let's say the photon is a ball, and it can rotate in this way, or it can rotate in anti-clockwise manner. So let's say this like has like some rotation axis in the middle, and just like very crude, like we could crudely say that, okay, if the ball is spinning clockwise, it has zero amount of information. If it's spinning the other way, anti-clockwise, it has one amount of information. So it's just arbitrary. For example, what you have in your classical computers, your laptops right now, what exactly encodes 0 and 1 is not like some, you don't exactly have 0 1 sitting in there, right? What you have is some kind of transistors, or basically some materials in which you say, okay, if this amount of current passes, it'll have 0, and if this amount of current opens up the transistor, and so on and so forth. But yeah, just no, I won't go into details, but essentially there's some physical thing in your laptop that is representing the 0 1. So it's the same with quantum systems. However, the outlier now is that there's this principle called superposition, where basically we're not just in 0 and 1, but essentially we're in a superposition of, we're essentially in a probability distribution over 0 and 1. So our state is not just 0 1, but we have basically alpha 0 and beta 1 state. So alpha and beta kind of dictate how much of it is in 0 and how much of it is in 1. So it's called probability amplitudes. But yeah, very easy way of thinking about this would be to think about a probability distribution over your qubit. So, and these numbers, alpha and beta, they're complex. So you essentially have a generalized idea of probability. Yeah. So we have some complex numbers that make up a probability. So basically alpha and beta have to, square to 1. So we'll go to that. So yeah, the same way with if you have more qubits, then you have not just 0 1 state, but you have all these binary possibilities, and 0 0 0 1 1 0 1 1, and then you have corresponding amplitudes for each of this state. So the idea is, without looking at the qubit, you cannot really know if it's in 0 state or 1 state. It has some kind of, like a probability distribution. And then you have to really figure out, okay, how much probability of alpha and beta really are. And this you do by measurements. So, basically, so the format here didn't translate, but essentially what it's saying is that now I say that a single qubit basically has a quantum, we call it a quantum state, which is basically a probability distribution, alpha, described by alpha and beta. And if it's a probability distribution, it has to, the sum of all probabilities have to be 1. So this basically is just saying alpha mode square and beta mode square have to add to 1. So just some typo here. So yeah, essentially we have states, or we can represent our qubit as like a vector, which has, alpha and beta 2 components, which it's just vector that lives in some like Hilbert space. And so that's essentially how you present quantum states. Very easy, just vectors. And the only like difference or outlying part is that these vectors are complex. So we essentially have like a general form of a probability distribution. So another very interesting thing, outlying thing, is that we are usually used to probabilities being positive. So we add two probabilities and they always add up, right? And but now we have something different. We have complex probabilities. So we have complex probability amplitudes. So essentially you could have positive and negative parts of the probability. So you could, this is what we call interference, essentially that you add two things and there could be some deduction and or subtraction rather than always adding up. So you can get interesting interference patterns essentially, and this is something that you wouldn't see in classical probabilities, right? So so these are all like very I'm only outlining the unique parts of quantum computing. And if you have questions, please you can ask. Okay, there has been some issue in uploading the slides, so there's some missing things there. Okay, no worries. So now we essentially can just represent the state as a vector. So this is just a way of sphere is just a way of representing one qubit state. So this vector, you can just picture it as like a arrow on the sphere. Which basically has to have norm 1. I won't go into details, but essentially what you're doing now, you have vectors. How do you transform vectors? How would if I have a physical system, I want to go from a certain state to another state. I'm doing some computation in my computer, so I need to transform the state. And that basically, I have to apply some matrices, right? So if you remember from your linear algebra, if you want to preserve your vector length, basically you do orthogonal matrices. And so in quantum computing, you essentially have complex vectors. So what you were working with is unitary matrices. So you just apply a unitary matrix, and it's going to transform your state. So just like a cube detail, it's not as scary as the terms are. So it's just like you apply unitary matrices and you transform your states. And then, so essentially, how do we in the end tell what state we are in? Is, you have, let's say I give you some arbitrary state, you have to essentially figure out what alpha beta factors are, right? And how you do that then is essentially by sampling from this probability distribution, right? You try to see the probability, you sample many, many times, and then you essentially are trying to reconstruct this probability distribution. So that's the idea of measurements, because we don't know what alpha beta are. And if we prepare the state ourselves, we might know, but essentially, the idea is that you're trying to reconstruct or get an idea of this probability distribution by sampling. And sampling here would then refer to measurements. So, okay, there's also, again, missing text. Maybe I should share my slides. There's some missing text in these. Well, this is not the most important, but if later on it continues, I'll just, share my slides from my computer. So another outlying factor that you might have heard of is entanglement. So essentially, again, I won't go technical, but it's another outlying kind of unique thing that is basically just correlations. So when you have many qubits, or you have more than one qubit, the correlations that they can have with each other can be quite strong and quite non-classical. So the way they can interact or have correlations with each other is something that we term as entanglement, and it's something, again, that is we do not see at all. That has no parallel in the classical universe. So so just to summarize, there's some exciting new things. We're working with like more generalized probabilities. We're working with complex vectors. There are some strong correlations possible. There's interference possible. So keeping all of these unique principles or factors in mind, we'll try to see what can we do with this. So what is the difference if I make a quantum computer made out of qubits rather than classical bits? So what is the difference? So I won't go into like the algorithms and all that, but what we are here for today is quantum machine learning. So how would a system that's made out of quantum physical systems, so qubits, how does that learn from data? And how is that, how is it a different learner from classical machine learner? So I'm sure everybody in the audience is like an expert in machine learning more than I am. So so machine learning is essentially, I'm just, one slide recap. We're trying to essentially learn from data. We make a parameterized model and we train it using the data. We have some kind of, problem in our mind. We optimize the parameters of the model so as to reach to that solution. So learning from data, how does it differ from a quantum learner? So basically, there are two different kind of, like I said, the history or the evolution of technology is still, it's ongoing. And right now what we have are small quantum systems, so what we call the NISQ era, like I said in the slides before. So essentially where we are right now is we have a very small number of qubits, up to like 50, that we can control, and it's still noisy. So we don't have perfect quantum computers yet. It's going to be a lot of work because it's hard to get noise out of quantum computers. And then I won't go into detail of that, but just to give you an idea, it's probably going to take 10-20 years before we have a very million qubits, just like your computer has. Like, we have terabytes of this and memory and computation power. So to get till there, it'll take some time. And what we have right now is some noisy, small quantum systems that are maybe up to 50 qubits or so. So given that, the question is that what can then quantum systems do with machine learning? And it's quite interesting because in machine learning, you already have the idea is that it's already robust to noise a little bit, right? You have data and you're trying to learn from it. And if the data moves a bit, there's a bit of noise and moves up and down, maybe the patterns overall are not switching so much. So there's still that's why there's been a huge kind of effort recently in the quantum community to understand it. Even with these noisy devices, can we already start doing something with machine learning? Because machine learning has robustness for noise, and maybe even if we use these noisy quantum devices, then we can already maybe start to see something. And the idea is to try to understand. So this is a new field, and we try to understand if, like I said, all of these unique properties, if they can sort of help us understand patterns in data that a classical computer cannot see, or if we can solve different kind of problems with this. So I'll give you some examples of that. So maybe I skipped this, but more technical. But yeah, an example is quantum kernels. So you're probably familiar with the kernel methods. And in kernel methods, essentially, we map our data, which is, it doesn't look very nice in the original space. And what we try to do is it map into higher dimensional space called feature space. And then we try to see, okay, now does it look better? Is it more workable? Is it more separable in this higher space? And then we apply these kernel methods to, speed up or get away with the competition. So a very interesting thing happens when we think about using quantum computers to learn with data, because what we're doing is we take data and we represent it as some quantum state. Now, I said that quantum state is essentially a vector that lives in a big Hilbert space, right? It's living in some vector space. So essentially what we're doing is we're mapping to some, it could be larger Hilbert space or it could be larger vector space. So essentially we're doing kernels here. And then when we try to work with these quantum states and see how similar they are to each other, what we're essentially doing then is, doing these quantum kernels is essentially we're just doing kernel methods. So this is a very interesting question. We're trying to understand that, can we, for example, have kernels that are classically not possible? Can we essentially define similarity metrics, or can see correlations that classical computers would not see? So yeah, this is an interesting question that we're still working on. I just would give like a very quick example. I don't want to go into details, a bit technical, but a very nice example that I go to work on was classification. So essentially, we borrowed like some very nice apparatus from quantum physics to try to classify our data. So we had classical data, we mapped into quantum states, and then we looked at there's whole apparatus of people or research over the last 30 years in which they look at how to distinguish two quantum states. So if I had state A and state B, how do I tell them apart? This kind of thing is set, it's already been done 30 years ago. So we try to see, okay, how does it look if we use a quantum computer to do classification? We essentially are doing quantum state discrimination, is called. And yeah, it's a very interesting example. And so I'm getting questions about if it's better, or how does it compare to the classical one. So I'm getting questions in the chat along the way. And yeah, so firstly, so far what we understand so far is that if you talk about learning from data in terms of sample complexity, generalization bounds, if you're talking about, if there's any speed ups that happen for different machine learning applications. So this is still in research. So far, we know that they're comparable sample complexities for both classical and quantum machine learners. But yeah, it's still under work. But even the idea of, just talking about what they call advantage, that if there is any advantage in using a quantum computer, there would be like exponential speed ups in, for example, classification or clustering or any other application. So these are sort of open questions, but also we try to, as academics, we're trying to understand if it gives us something different. It's a different kind of computation paradigm. It's a very different computer. It's not just about speeds. It's like comparing apples and oranges. But yeah, it's definitely a lot of people in the industry would be very happy to know that if there's some kind of application where we get exponential advantages. But it's still under research, and also everything is not about advantage for now. But yeah, I think there could be interesting uses for optimization and for yeah, I already come to optimization example. But yeah, for maybe when we have error corrected quantum computers with less noise, we might be able to actually do a lot of cool things with cryptography, with their search algorithms, their factoring algorithms that require these error corrected computers. That would be yeah, quite that would be the revolution, really. It would be important in designing new materials and so. But for now, we're talking about quantum machine learning and noisy quantum computers. And with that, we can still at least compete with classical sample complexities. But yeah, but that's not just the idea, right? We're not just trying to say, okay, we can compete or not. Okay, so maybe yeah, maybe I won't go into detail of this because there's not so much time. But yeah, I just I'll have some examples outlined here about different kind of algorithms that that we borrowed or are building on top of classical machine learning algorithms. For example, this QPCA is the quantum principal component analysis. So the underlying, so it's the same idea. We want to do principal component analysis, but we do it on a quantum computer. So there's possibility of speed up here if we have quantum memories and if we have an error corrected computer. But for now, it's not doable, but very, very amazing sort of application. So these are sort of different examples. Then the other side of the coin that I talked about, where machine learning tools are actually helping us understand physics, which is extremely interesting as well. So for example, I found this really interesting paper where they made this sort of neural network to guess where so it was a study of the solar system, and they're trying to see, okay, if we give it data about where the sun is, where Mars, and how we see sun and Mars planet from Earth, so we give it like angles, how would it be if the neural network is able to learn the physics? We give it data, we train it, is it able to learn the dynamics of the planets? Is it able to predict where would we see sun and Mars later on at some other point? So really, really interesting. Can have a lot of interesting applications. Maybe in the future in the schools we don't teach just classical mechanics of how we study how planets go around Earth, the moon, what was about the sun, but we actually are we also have some neural networks that represent our parameter. These are models that are sort of representing our knowledge. So very very interesting time to be living in. So another very interesting example is quantum state tomography. So I said in the beginning that we represent our states as these vectors, and you saw that even for 2 qubits, when we had like just 2 qubits, we had a 4-dimensional vector. So it scales exponentially with the number of qubits. So now if I give you a very large number of qubits and say, okay, what is the state? You have to do a lot of measurements, right? You have to do exponential number of measurements to figure out all these alpha beta factors in your state vector. So this is what is called tomography. It's trying to understand what state we are in. So essentially, if you just, if you don't have machine learning, what you have to do is do many, many, many measurements and collect your statistics to see what kind of probability distribution you're working with. But now what you can do is essentially train a neural network, for example, to sort of you give it a bit of measurement data, and it tries to guess what state you're in. It tries to reconstruct or give you the rest of the statistics. So this is really helpful because generally doing state tomography is very expensive. So yeah, just a small example, but again has a lot of wonderful impact and applications. I put some more applications here where, for example, they recently used a neural network to sort of predict where new kind of supernova would be in the universe around us. So they gave it some data and trained it to sort of predict the kind of supernova we're looking at. So this is just so many kinds of applications that can be there. These are some more technical examples on the side, but yeah, there's just endless amount of things that we can do. So yeah, it's both the fields are kind of feeding into each other. For example, there's so much we don't know about neural networks and how they work, and a lot of people from physics are trying to understand how neural networks are functioning, and they use tools from statistical mechanics and physics to sort of understand using entropy and energies ideas to see how neural network is actually working. So there's a lot of looping and feeding in the both in both of the fields, which is really exciting for all of us. Okay, so I'll continue if there are no questions to this part. If there are any questions for the slides, there were general questions about the field, but okay, so somebody's asked, I can take this in the end, how QML is evolving. If there are any other questions regarding the slides for now, we can take the general questions to the end. Okay. Okay, so let's also face the other challenging part of our careers as being women in physics or in computing, in any I think STEM career. Whether it's in industry or academia, it's we all have some kind of weight on our shoulders when we are working. It's like we are representing our whole gender, and we cannot make mistakes. And there's usually, a lot of pressure. So, for example, I put this code here I found from this very wonderful physicist. She works at Imperial College in London. And she's like, there's not so many women in physics, and you sometimes find, you're struggling with unconscious biases, and yeah, it's just a lot of extra burden to carry along with your work. So yeah, we can talk about that a little bit, and also later on maybe in the discussion session. But yeah, so I don't know if you can see this properly, but the percentage of women so the lowest three lines are physics, engineering, and computer science. And although the numbers have increased over the years, it's still it's less than 20%. So especially in physics, we have consistently stayed, whether it's undergraduate, master's level, PhD level, and for professorships, it's very small number of women at the top positions in academia. So yeah, in physics, it's definitely much worse than, let's say, like biology or computer science. But yeah, it's something we need to talk to with each other about. And it's not just women who need to fix this. We all need to fix this together. It's not just our problem. It's the whole society's problem. So I found this really interesting kind of survey that was done by, I think, American Institute of Physics, and they had 2,000, less than 2,000 participants. I have the statistics here somewhere. So yeah, so they got 1,700 responses, and what they tried to do was like get the frequent sort of words that are used. If you ask them what helped them succeed, then in the responses they try to just figure out what is the most frequently used word, or themes in their discussions. And yeah, it's interesting to see that women, although both the genders talk about in their success, hard work is important, mentors are important, but women sort of give a lot of weightage to friends and family, that or my family was very crucial in helping me succeed. And men tend to talk about how their other experiences, or getting more experiences in their field, is able to help them succeed or get better jobs. So just interesting, like how we deal with, there's a bit of how we deal with the social, or there's a social aspect to our experiences. And then again, the second question is, how what were your barriers, and what is something that you had to face, like difficulties in your careers. And so the bold one is the differences. Again, like men usually tend to focus on, okay, maybe I didn't have good administration around me, but women would have, they, let's say, they would say, I didn't get enough funding, or they had gender bias. So for example, I've personally met many women in physics at different conferences, and it's yeah, they would tell you that, it's they won't get funding, or they won't get a job because they're at a certain age of their life where they're expected to start a family. So the employers would be hesitant to hire them, because then they might start a family. And but we all have to do that. So yeah, this kind of, or gender bias, where in physics a lot, I think in computing generally it happens a lot, that you face this unconscious kind of bias where you're not respected equally. If something good happens, it's good, but if something bad happens, it's like, okay, all it goes on to all women. And you have to get, you have to put in a lot more effort to get the same respect. So these are things that need to be talked about. And yeah, another very important factor is harassment, which you might think it's kind of getting better, but there are a lot of cultural differences here, of course, as well. Like, from Pakistan, it's very different from here and in Europe. But definitely, this the degrees of this could vary, but it's definitely, it's up to. So they did this survey I post here from 2019, this American Physics Society, and I think they report like up to 90% of the women they surveyed reported that they were harassed. So of course a very discouraging factor. I personally know women who dropped courses or changed their lab partners or their mentors because they were having these issues. So again, something that needs attention of the whole society. So just going forward, how we can firstly, how we can deal with this is talking about this. Especially harassment is something that probably wouldn't be reported very. There would be a very large dark statistic there that's not reported. And but it has to start young, and it has to start with families and schools and education, and for everybody, that you kind of try to change the biases, that it's not just science is not like just for women, it's just for men, it's for everybody. It's just and we're trying to understand nature and trying to make a good impact. So it's just curiosity rather than some kind of ability. You're not born with any of this, right? When I tell people I am in physics, I usually get this, oh, you must be really smart. I'm like, no, I just have been doing it for 10 years. I got better over time. It's not like I'm born with something. So I think it's not really about ability, but hard work and curiosity and passion about being, in this fields. So yeah, and also of this popular construct of, you must be genius to work in this is very discouraging, especially how it's portrayed in the media. And you see even very young girls, even at school level, start to like go away from science because this is huge pressure of always being, exceptionally good and exceptionally brilliant about something. You're allowed to make mistakes, and you're learn, and the only only thing that gets you going is essentially just staying passionate about your work. We all are just learning it. So yeah, these are things that I think would be important to discuss and work on as community. So yeah, in the end, I just mentioned this quote. It's kind of just a summary, that imagination is more important than knowledge. We're not really born with the knowledge, we acquire it with time, like I said. And yeah, it's if we stay curious about it, we'll all get there. So yeah, thank you so much. I went a bit over time, but yeah, if you have any questions, please feel free to ask. um, yeah, the floor is open. Thank you. Okay, so Hamna is asking how QML is evolving. So it's a young field, but it's evolving really fast. Um, like I said in the talk, it's we are trying to understand how what are our sample complexities for different kind of tasks or algorithm machine learning tasks at hand. How do they generalize? What kind of kernels do we use? How do we present data in as quantum states? All of these are being worked on. It's evolving really fast, and I think it's still quite young, and there are a lot of open questions, especially about the advantage that I mentioned. That is there any advantage to using quantum computer to do machine learning? We're not sure yet, but I think as quantum computers become less noisy and become, we can do error correction or fault tolerance for them, then there would definitely be a whole lot more impact, because there are a lot of algorithms or linear algebra routines that you can you can speed up just by using a quantum computer. So I don't think that we're going to replace the whole classical system. I think how you use so there's like a conjecture in the quantum community for now that we'll probably have like an accelerator on the side, like a quantum accelerator, like how we use QPUs. So we'll like plug into our quantum computer for extra help for certain, for example, linear algebra routines, but not for everything. So it doesn't make sense to, for example, do some, I don't know, let's say some kind of classification task on a quantum computer, but for some other task or a part of it, there would definitely be speed ups if we use quantum computers. So a lot of people are working on it. The experimental and like the it's and the advancement is getting it's going really fast, and it's a lot of hard work. I respect them a lot, and yeah, but I think exciting things are we're already in the exciting part, and they're gonna get only more exciting in the next 5 to 10 years. Okay, any other questions? Okay. If there are no other questions, then I'll end the session. Should I? There were some questions along with the talk, but yeah, I think they were quite general, and I've tried to address them in the end. I hope you're. It was a very general talk, and I hope you're at least excited about something that is probably going to be also impacting your work in the future. And yeah, there's a lot of interesting things to work on for us, and to understand our own capabilities and nature's capabilities and how we can use them. So yeah, thank you so much everybody for listening. Yeah, hopefully we see you soon again at the next event from our Pakistani Women in Computing chapters. So yeah, thank you so much. I hopefully see you again. Bye bye.